Okay, so we continue. So we move on to study lecture 3 in session 4, which is about the network interface to digital sensor, right? So you remember today's topics is about the sensor in IoT. And we know, okay, there are two types of a sensor. One belong to the category of analog sensor, and the other belong to the category of digital sensor, all right? And we also know that the microcontroller by default could be considered as a built-in sensor for voltage, because microcontroller allow you to convert analog voltage into digital number, right? So this is why we have spent lecture 2 to study the way of interfacing analog sensor. As long as we are able to convert the value of a measurement of any physical quantity into voltage, then we can use microcontroller to do the conversion from analog value into digital number, all right? So now I guess you should believe that by default, a microcontroller is a digital sensor for voltage, all right? And the good news to you is with ARM Cortex microcontroller, all right? Each microcontroller can interface with 12 analog sensor, right? So, and besides that, so inside the interface to analog sensor, you have 8 sampling device, you have 2 quantization device. It's like you pay a price of a bicycle, you get the sport car, all right? Now we continue. And interestingly enough, right, microcontroller by default is also a digital sensor for measuring velocity of a square wave. If we are able to convert any physical quantity into square wave, right, then we should be able to measure, okay, that physical quantity with the use of a microcontroller, right? For example, we can even convert distance, the value of a distance into square wave. So that is a sensing principle or design principle for laser rangefinder or acoustic sensor, ultrasonic sensor, which allow you to measure the distance, all right? So that is a typical example. So you are not only restrict in doing the conversion of a motion of a rigid body into the motion of a square wave, all right? So any physical quantity on the measurement, all right, could be eventually converted into a velocity of a square wave. Then by default, microcontroller is also velocity sensor of a square wave, right? So then you see, really is very beneficial for you to study a single device, which is a microcontroller. Then you know a lot of a possibility, right? Okay, so we continue. Then for this hardware module, actually it's not that you pay a price of bicycle, you get the sport car, but this is a situation like this case that you pay the price of bicycle, but you get a motorcycle, all right? And this is because microcontroller ARM Cortex M4 allow you to interface with 2 digital sensor, okay, but not the 12, right? 2, but not 1, but the 2, right? So in this case, immediately you understand this should be slightly simpler than the case of doing interface with analog sensor, right? So this lecture should be quite simpler, right, than lecture 2. Okay, so first look at the application of a digital sensor, right? So Actually, there are two types of digital sensor. One is if let's say the sensor itself output digital pulse, but this digital pulse has a meaning. It's like in lecture 2, we have seen this temperature humidity sensor, and the inside you have a built-in mini version of a microcontroller. Then output here is also square wave channel, but this square wave actually carry information. So like in this case, we just treat this as a data, but don't treat as a string of a square waveform, right? Okay, and then for the encoder, for example, here, then you may see, and all the sensor inside basically output a string of square wave, right? And this is needed for achieve these kinds of linear motion controller. If you see this video, and this actually is a linear position control, right? So for those of you, if you have a study advanced control theory, then you may see normally for position control of the motor, we always have the inner velocity loop, outer position loop. So it is then you see it is always good for a sensor to output both velocity information and position information, right? So this is a typical application scenario. And here also you see is a rotary motion. This robot can perform is a rotate articulated motion, all right? Okay. So you see all the joint basically perform angular motion, right? So previous example is a linear motion, and in this example you see rotational motion, all right? And in manufacturing industry, many motion are this type of a motion, all right? So it's a rotary motion, okay? So then here is one more example. You see play game with a robot and robot arm. Actually, in this case, also perform rotational motion, right? So from here you will see this lecture is very useful for you to understand robotics, right? So inside robotic arm, we have a lot of this type of a sensor, right? It's a digital sensor. And especially for rotational motion, because the robotic arm, you have a lot of joint, right? Each joint is under control of one single motion control loop. And inside each loop, you must have one such sensor, right? Okay, so it should be good enough for you to know this. And one more example. So Sam, inside this robotic arm, there are a lot of digital sensors, all right? Okay, so it's just a short video. And then here you see we have a lot of mobile robot, AGV. So you see for the control of mobility, so these are the typical example of mobility. So previous example showing you manipulation. So you see you have a mobility related motion control, manipulation related motion control, all right? So inside this control loop, you will see the presence of a digital sensor for the measurement of a velocity, all right? So it should be good enough, okay, for you to see, all right? So then what is the motion in space? Basically, is a change rate of a position, all right? So then motion may refer to linear motion, angular motion. Basically, these are the two basic type of motion. If you combine these two together, you may see circular motion, right? That is a combination between angular motion and the linear motion, etc. Right? And in robotics, right? So there is a wide use of digital sensor for the measurement of joints, angle, joints, velocity, because we need to measure, you see, the theta one dot. Theta one dot means velocity of theta one, all right? Then theta two, theta n, because a robotic arm may have an n degree of freedom, right? So then you need to have an n such a sensor to measure all this velocity. So you see, so this lecture is very, very relevant to the study of robotics, right? But of course, it's relevant to IoT because for internet of sensor, internet of actuator, we may have a digital sensor. Then we need to know how to interface with them, all right? Okay, so then for motion related sensor, so we have a position sensor, velocity sensor, acceleration sensor, all right? The popular one in robotics, in industry, should be the velocity sensor. And the reason is because of a low cost. Another reason is because we can also obtain positional information from this sensory output, right? And in industry, the common name is called as an incremental optical encoder. Okay, why we call optical? Because we use the light emitter, light detector for us to convert angular motion, linear motion into a stream of a square waveform. All right, so that is the working principle, right? So use a light to convert it into square waveform. Why we call encoder? Then it's because in the disk we place regular hole. It's like a pattern. It's like doing encoding, right? Spatial encoding. So this is why I call it an encoder. Why we call incremental? Because we only measure displacement. Accumulation of a displacement within the time window divided by time is average velocity. So incremental means we accumulate the displacement. Then we know the displacement within the time window, right? But if we have a reference position for us to start the integration or accumulation, then the result will be position. It's like doing integration, all right? So from the keyword, actually you can find out all the physical principle behind the design of these kinds of interface, right? Okay, now the good news to you is Cortex M4 support the implementation of interfacing with digital sensor, right? So then why do you use ARM Cortex? The answer is what? With a single controller, we are able to build up a network of communication, network of a sensor, and the network of actuator. Because next week you will know, okay, with the same microcontroller, we are able to build up a network of actuator, right? Then what is your role? Okay, your role is just as a user. So we just position us as a user. We use a microcontroller, right? As a user, you should not ask the question of why. Why is in this way, all right? So you just follow instruction, okay? Just use, by following the instruction, then you just use the microcontroller in this way. That's it, all right? It's like when you buy a car, you just use the car. Don't ask a question why this car has been designed in this way, all right? Okay, so then in order to fully understand the usage of a microcontroller, you need to spend at least one semester to study microcontroller, which include the programming, part and the interfacing part, right? Programming part means how to read in the data, how to process the data, how to produce, output the data, right? So that is a programming part. Okay, interfacing part means how to interface your microcontroller with the input device, such as a sensor. Keyboard is also an input device, right? Sensor is just one of them. And how to interface your microcontroller with output device. Motor is one type of output device, all right? To turn on the lighting is also output device, turn on the light, etc. Emit a sound, right? Is also output, right? So you see, just know how to do programming, how to do interfacing. That's it. Okay, as a user, you just need to know, okay, how to program microcontroller, how to interface a microcontroller with external device. That's it, right? Quite straightforward. Then the skill for you to have as a user is also very simple. You just need to know how to configure the hardware module inside the microcontroller. That's it. Then the hardware will do the job for you. Okay, it's like you just need to know as a driver. You do not need to know how to design a vehicle. You just need to know what is the traffic rule, all right? As a driver of a car, you just need to know what is the traffic rule. Then you drive your car. That's it, all right? Okay, so for this one, similar like a driver of a car. So user of a microcontroller just know how to configure microcontroller. Then the tool for you to configure microcontroller, you just use one of these three instructions, right? You move a value into a memory address, that's it, all right? So then automatically you configure the hardware. The hardware will do the job for you, right? Okay, then for the interface with a digital sensor. So you remember, digital sensor means is a sensor which allow you to convert, okay, value on the measurement into square wave, right? The value on the measurement could be velocity, position, distance, whatever, right? Then the output is a square wave, right? Once you have this digital sensor, then microcontroller can, one microcontroller can interface with a tool, because the microcontroller for this one has a tool, QEI unit, right? Okay. And this one has a built-in integration function, so you can read out the position information. And actually, this one is a timer. Basically, it's a counter, and has a timer, define a time window, then count the number of pulse, etc. Right? So then for your digital sensor, so you remember lecture 1. What is a digital sensor? So we use this motion sensor as example, okay? So it's this device which will transform rotational motion or linear motion into square wave, right? So in particular, we have 3 pair of light emitter, light detector, right? 2 pair of them are needed for us to know the value and the direction. Direction means a sign, positive value, negative value. And the third one is for us to know the reference position for us to start to do the measurement of a velocity. If we know the 0 position, then we can do integration. Then the result will be the position or distance, something like that, right? So it's quite straightforward. So therefore, so the digital sensor will output 3 square waveform, okay? So we have a signal A, signal B, plus another one is a reference, but it's not shown here, all right? But this blueprint basically showing you, okay, just now I already mentioned, it's like in this case, you just imagine you pay a price of a bicycle, you get the motorcycle, right? Motorcycle is a slightly more complicated than a bicycle. For example, you can invert the signal. Let's say you have a positive pulse, and then you can get the negative pulse. Or your sensor, let's say you output, for whatever reason, you only output negative pulse, then you must invert it into a positive pulse, all right? Another function is to swap, okay? Now you say this is A, signal B. Actually, by software, just consider, for whatever reason, signal A suddenly becomes signal B, B become A. Then in your program, you have this flexibility. Okay, consider A as a B, B as a A. That's it. So you see, it's like you pay a price of a bicycle, now you get the motorcycle, right? Slightly complicated, right? And also this slide basically showing you that you are able to count a high speed, high velocity, because this one has a velocity pre-divider. So it means what? The velocity here, velocity of the square pulse could be very, very high, because this allow you to choose a divider to slow down the counting pulse, right? So without the changing the hardware, so this interface allow you to interface with a high speed velocity sensor, all right? That's it, all right? And here implementation actually is very simple, because for velocity sensor, you remember lecture 1, we just have a counter to count this number of pulse. Each pulse corresponds a displacement. This displacement could be angular displacement or linear displacement, all right? Then we define a time window or a measurement period. So we use this term, a measurement period, all right? So this value actually is this value, low, okay, use this term. And the timer is automatically is a counter, right? And what is the actual measuring time? Because we need to, after this amount of a period, we do a reading, okay? Let's say 10 milliseconds, we do a reading, or 1 millisecond, right? But you can also do a reading earlier, because you get access to this one. So that is what is the actual value of a C, okay? You may get the C, which is the value at the end of a data T, or you get the C, which is a value, okay, just before data T. You have all flexibility there, right? Then what is the maximum position? Because this is to set the overflow. Let's say I only measure maximum position from 0 degree to 360 degree, John, right? Full rotation. Go beyond that, then consider it's 0, reset to 0, right? Something like that, right? To set the position limit, right? And just from the name of a register, you see how to operate it, all right? Okay, so this one allow you to, you pay a price of one bicycle, actually you get the motorcycle, means you get house 2 sensors, slightly complicated, all right? So not so complicated. Then you see this index from the 0, 0, 0, 1, 1, 1. That means for one sensor, you have a 3 signal. Then you have a 6 signal, then you have a 2 sensor, right? Then the physical connection to the pin of a device is here, the chip, okay, pin 5, pin 64. Then meaning of this pin is a port, which pin of which port. This means pin 4 of a port F, pin 3 of a port D, pin 4 of a port C, pin 0 of a port F, pin 6 of a port D, etc. Right? So this table help you to do the physical connection. So you should not make a mistake when you do the connection. All right. After the physical connection, then you just focus on the configuration. All right. Then how this QEI works. All right. So basically, if you're taking the 2 signals to determine whether it's a clockwise rotation or counterclockwise rotation. So you see, basically fully implement the working principle that we have studied in lecture 1, right? So you just exactly use that principle, implement it by the hardware, right? So that gives you the confidence about the power of this microcontroller, okay? That's it. Then change of direction. So basically you implement this principle, right? So then as a user, once you are confident that this guy or this module is very useful for you to interface with the digital sensor for the measurement of a velocity and the position, then you just know how to use it, all right? So the procedure is same, configure input, configure internal process, configure output, then run this module, that's it. And the good news to you is this one is not so complicated compared to the interface that you have just now studied in lecture 2, right? Is much simpler in this case, right? Because we only have 2 sensors, right? And inside just 1 counter, all right? Just a counter, right? So it's very, very simple, okay? Person to decide is observation time window. So time window is in terms of number of cycle time. So number of cycle time per unit of time. So unit of time means 1 second, right? And what is cycle time? If let's say your microcontroller system clock is this frequency, 1 over frequency is 1 cycle time. Then the number of a cycle time, because each cycle will count by 1, because you see timer is here, timer, all right? Then the period is equal to the number of cycle time. So you must determine what is this value, right? Because this is decided by you. If let's say I want to have the reading every 1 millisecond or every 2 milliseconds, every 5 milliseconds, up to you. So this is a user decide the value. Then we need to calculate what is this guy, use this equation, what is rho. Then this value will be written inside here. All right. Since we have 2 interface, we can take in 2 sensors. So now you see, actually you have a 2 unit of this digital sensor interface, QEI 0, QEI 1. Okay. So then you have you can have a different rho value. Your observation time could be different. All right. So this is the first thing to do. Actually, is to set the data T. Where is the equation? Equation is here. Is here. Actually, is to determine what is data T. All right. Very simple. Then next is to just get this number, count, get this value done already. Because we cannot set this one. So you can see this sensor just output velocity per unit degree or per unit meter or per unit distance, right? Or displacement. Per unit displacement, this can be angular displacement or linear displacement, all right? So just consider by default 3 as a 1. And since once you implement it, because based on your physical system, you know, because when you buy the digital sensor, the sensor will tell you what is data P. Then you get this value times data P, you get the exact velocity done already, all right? Okay, so this is just for you to know. So it's quite simple. First, to set the data T is a low value, right? Simple. Okay, internal process. Okay, whether you want to, what will be the divider, slow down, enable this microcontroller to measure high-speed rotation. Then you just set the divider here, enable this sensor, you set this speed to be 1, right? So this is to determine the direction of rotation, the sign, positive sign, negative sign, how to determine the sign. Use signal A, signal B, right? And whether you want to swap the meaning of signal A, signal B, enable the interface with the digital sensor. This is to do a little bit of filtering of enable the built-in hardware to filter signal A, signal B. If let's say your machine is working in a noisy environment, they may have some noise. You can turn on, enable the built-in noise. All right. This one is to your software must do the setting. That means if you debug your hardware, temporarily you stop your machine, then you stop your sensor, all right? But don't lose the data. Inverse, you can basically is for the reference pulse. You can change from negative pulse to positive pulse. Signal B can change from positive pulse to negative pulse to positive pulse. Signal A just invert the meaning, right? So all this has been explained here, right? And the capture mode by default is age, only one signal, because when you do the counting, you just use a single signal. Actually, you can use 2 signals to double the resolution, right? So that means both signals will trigger the counting, right? So you have this flexibility. This one is to reset, okay? Once you set the right one, just reset the counter, right? To be reset the position counter, right? To be 0, okay? The rest I already tell you, okay? That's it. Then this is an interrupt because hardware, when they detect the reference pulse, they will tell you, all right? Then the timer reach the maximum or reach zero, they will tell you. When there's a direction change, they will tell you. When there's an internal error, they will tell you, right? So this is internally generated signal for you to know the working condition of this hardware, right, etc. Then output should be easier. Output, first, you need to set the maximum output, okay? Because you may say, I only get the maximum output of a position, notary position, 360 degree, all right? Then you can get all the output from here. What is a count, the C, right? And what is calculated, nominal speed per unit distance, right? And the actual position per unit distance. This is the actual position, right? Because we do not know the absolute position. This is or another way to say is a unitless, okay, position value, unitless, okay. Unitless means without the unit of a measurement, because we do not know what is data P, right? So this is a value without the unit of measurement. This is velocity without the unit of measurement, position without the unit of measurement. Once you know the parameter of your exact sensor, you just time that value, you get the exact speed and the position. Then you just run, all right? Once you run it, so you know the position from this position register is here, right? Is this guy, right? Then you have a tool interface. This is why you have a tool list register, okay? Actually, this guy basically telling you the uniqueness of this value, because you do not know this one. Once you know your sensor times this, you get this, okay? So it's writing here. You basically reading is a position without the unit of a measurement. All right. For velocity is the same. Okay, you get the velocity is here from this register. All right, get this. So you get the velocity without the unit of measurement. All right. Once you know data P, you time it, then you get the exact value of a velocity. Done already. You can also know the what is the observation time window. Okay. So this is by default, this is the data T. If let's say you get this number ahead of the time, you don't wait for let's say 10 milliseconds, you just half of 10 milliseconds if you want to verify. Then you get this data T. This is a real-time data T. Okay, by default, this data T is equal to low value. But if you read from here, actually you get this value here, right? So you see, you can get the maximum value of a data T or the actual value of a data T, right? Done already. And then this one, you can get it from the counter, okay? This is the actual value of a C, or you can get the maximum value of a C as well, all right? So maximum value of a C is when the counter, that means the timer reach this value, then the value of this one, okay? So you can, is a period, right? Something like that. Okay, then done already. Then the rest is interrupt. They will tell you whether I detect the presence of a reference. This is a zero position. Okay, this just for you to know the zero position of your sensor. All right, or the timer reach maximum or minimum. There's a change of direction or not, or some error, internal error. All right. Okay, so you can read all this meaning. So I guess you can also clear the interrupt, right? Read the interrupt and reset the interrupt, etc. And know the status, okay, of operation. Okay, this also indicate whether there's an error and whether now is continuously running in the clockwise rotation or counterclockwise rotation. Just know, okay, direction of a motion. Read this one. Interrupt means here is to tell you there's a change of direction, right? Okay, so you get all the data. Okay, then these are the small exercises for you to understand the working principle of digital sensor, and you verify, then this test your understanding. Okay, so solution is provided. Okay, so let's go for the study of lecture 3. Okay, so by now we have completed the study of session 4, which consists of 3 lectures. We just slightly overrun the time, right? But it is good. So by now you should have more confidence about your skill, your knowledge for the construction of IoT. And since robot is a mini version of IoT, then by now you should have more confidence about the design of a robot. And the automation system, control system are also special version of IoT. Then by now you have a more confidence about the implementation of automation system with the use of ARM Cortex microcontroller. Right? Then next week we will study interface with actuator. So after next week study, I guess you should be totally confident about the design implementation of a robot system, design implementation of a control system, and the design and the implementation of an IoT system. All right. Okay. So thank you for your attention, and you can try to formulate your question, right? Then next week at the beginning of the lecture, we will do a short session of Q&A. All right. Okay. Thank you for your attention, and see you next week. All right.